Okay, so today is the last lecture of the first part of the Foundations of Intelligence Systems. So far, just to recapitulate, we have had 2 sessions on regression, 1 session on classification, and then 3 sessions on statistical learning theory. So I hope that by this few lectures you were able to grasp a bit some of the fundamental ideas of machine learning, and especially the theory behind most of machine learning algorithms. So today we will close this first part with a lecture on the support vector machine and a bit also I will mention a bit kernel method. If you remember, I introduced already the support vector machine in the classification lecture, but it was done quite quickly, and I just gave you some hints on how and what kind of linear hyperplane was computed by the SVM. Today we will go a bit deeper into some of the optimization background, optimization techniques that are needed to compute actually that separator. And then I will mention briefly also kernel methods at the end of the lecture. So if you remember what the idea of SVMs was a few weeks ago, it was that, of course, if you have linearly separable sets of points, so there's blue points and red points there, and then you can split them with a line in the middle, then there's many ways of doing so. And the support vector machine viewpoint is to maximize the margin. So what is the margin? The margin is the length of the width of a tube that you can fit around a hyperplane, and then you let that margin expand as much as possible. And once you touch points on either side of the tube, then you have the width of the maximal tube. And if you just select this criterion to choose a hyperplane, usually you want to maximize the margin. Basically, you want to find the largest width as possible to choose the hyperplane. So once you have done that, the points which touch here the margin, so which touch the tube here on both sides, are called the support vectors. I think you remember this from last time. So what is exactly the problem that we want to solve in equations? Well, we have a training set of points x1, y1, xn, yn. Each x is a vector, each y is a label, binary label -1 or 1. And we want to find a hyperplane that separates both. That's the first condition. And finding a hyperplane that separates those 2 sets is equivalent to finding a normal vector w and a constant b, such that w transpose xi plus b is positive for all points such that yi is equal to 1. And that number w transpose xi plus b is negative if yi equals -1. So this is just the fact that we want to have a hyperplane, a separating hyperplane. Now, let us formalize the fact that we want to have a hyperplane that maximizes the margin. That is, it has the largest room around, basically the hyperplane, there's the largest room as possible before we touch any of points on both sides. So because a hyperplane defined by a vector, normal vector w and the constant b is the same as t times w and d times b, we lift one ambiguity here in our parameterization by saying from the start that we will consider a hyperplane w transpose x plus b equals 0 here. This will be the hyperplane that we will be looking for. And then we will set the tube to be exactly defined on both sides by w transpose x plus b equals 1 and w transpose x plus b equals -1. So once we have parameterized our hyperplane in the tube that goes with it this way, what we can see is that the distance between the hyperplane and either of the tubes is basically is basically the inverse of the norm of w. How can we get this? Well, let's choose any point on the hyperplane. Let's call it x1. Let's choose another point x2 on either of the tube sides, and let's call it x2, and we want that x1 and x2, x1 minus x2 or x2 minus x1 is collinear with w, okay? So the first point belongs to the hyperplane, so w transpose x1 plus b equals 0. The second point belongs to one of the tube sides, so w transpose x2 plus b is equal to 1. We chose it here on this side, so w transpose x2 plus b is equal to 1. If we subtract both, we just simply get that w transpose x2 minus x1 is equal to 1. And since w and x2 minus x1 are collinear, we just simply have that the product of the norm of w times the product of the norm of x2 minus x1 is equal to 1. And we know, remember that we know that we just simply have then that basically this length here is 2 times the length from x1 to x2. So we just have that the width of the tube, the margin, is just simply 2 times x1 minus x2 norm, or 2 divided by w norm. Okay? So if we parameterize our hyperplane in the tube this way, a w which has a small norm will imply a very large tube. Okay? If we let w go to infinity, then it basically means that we have no tube. The hyperplane is confounded with is the same as the tube itself. So now that we have set up those very simple quantities, the problem is the following. Basically, we want to find a hyperplane which splits the data. So again, splits the data means w transpose xi plus b is positive. Sorry, here. It's not just a splits the data. We want to find a hyperplane whose tube splits perfectly the data. That is, we want not only that the hyperplane, all the black points are on one side of the hyperplane and all the white points are on the other side, we also want that the black points are on one side of the tube and the white points are on the other side of the tube. So we want all points here to be such that w transpose x plus b is bigger than 1. Okay? So we want positive labels such that w transpose xi plus b is bigger than 1. Negative labels, w transpose xi plus b is smaller than minus 1 on either side of the tube. If you just put this together, it's just simply that yi, the label, times w transpose xi plus b is bigger than 1. So let's sum everything up. We want the tube to be large. The width of the tube is 2 divided by the norm of w. So we want to maximize the inverse of w, and that's exactly the same thing as minimizing the norm of w or minimizing the squared norm of w. So we want to minimize the squared norm of w, given that we can guarantee that yi w transpose xi plus b minus 1 is non-negative. So minimum of this such that this is an optimization problem. And the variables are, we have 2 variables, w, a vector, and b, a constant. So we need to find w and b which satisfy this. So this is a classic, we call it, I say classic, but if you don't know what a quadratic program is, it's easy to see why we call this a quadratic program. Well, the objective is a norm of w, okay? So the squared norm of w is just simply the sum of yi squared. Okay, so we want to minimize this, and with the constraint that for all I equals 1 to n, we have n constraints, n being the number of points. yi w transpose xi plus b minus 1 is non-negative. Okay? So the minimum here, the minimization, is with respect to W and B. Okay, so this is W. We have here W's and B's that appear here. If you look at this function, what can you say about it in terms of W and B? It's a quadratic function. It's a quadratic function, a polynomial of the Wi's. What can you say about this? Well, this is a linear function of the Wi's and of B. So this is a quadratic constraint, quadratic program with linear constraints. Quadratic objective with linear constraints. So usually it's called a quadratic program. So how can we solve this? Well, what we know is that there are lots of solvers to solve this. So if you just open a toolbox in R or Python or MATLAB, you will find many programs, commercial or free, which do exactly this, which are able to find, given those constraints here, exactly the W's. It's not always a very easy a program that's particularly easy to solve, because if you think about this, what is n? N is the number of points. In a typical setting, maybe n will be 10,000, 100,000, 1 million points. And so this basically means that you have to ensure for 100,000 or 1 million constraints that W satisfies each of them. And then at the same time, you have to find a W which has a small value. So this is one of the reasons why people have tried to see whether there was a way to reformulate the same program in a slightly easier or more in a way that's more easy to optimize, basically. So this is the idea of duality in optimization theory. So I will not assume that you are familiar with this idea, with the concept of duality, but I will walk you through one example here for the support vector machine optimization. So let's recapitulate. We have to minimize here. I just put 1/2 here because it's usually a bit easier afterwards, but minimizing the norm of W or square or the 1/2 is the same. So we're minimizing half of the norm of W under those constraints. So if you think about optimization theory, you have an objective. So usually we have to deal with a problem which is a minimum over x of f of x. So we call it f0 of x such that fi of x is negative. So you can put most mathematical programs in this form. Okay? The previous one here, this one maybe doesn't look like, here it's negative, here it's positive. Well, we just multiply this inequality here by -1 and you get what you want. Okay? So we're always trying to minimize a function of x with some constraints. Which means basically that, for instance, if there's a point here, if there's no point that satisfies all these constraints, basically this program has no solution. Okay? So the approach taken by duality is to say, okay, rather than assume that I would really want each of those points, each point x to satisfy each of the constraints here, let's put a price on each constraint. And whenever this constraint will not be observed, will be violated, then this will appear somehow in the objective. So again, the idea of duality in this case is to say that instead of looking at the constraint set as a binary set, if you want, it's either I satisfy all the constraints or I don't, we're going to introduce a vector of prices, alpha I, which are called Lagrange multipliers, which will somehow weight how much you are violating each constraint. So let me just give you the formula, maybe that's easier to picture. So we're going to introduce one dual variable alpha I for each constraint. So there's exactly n alpha I variables. That's one constraint for each training point. And we're going to form something called the Lagrangian. And the Lagrangian is the following function. It's the objective minus here each constraint weighted by a weight alpha I. Okay? So what happens when W transpose xi plus b times yi minus 1 is positive, when this is positive? Well, remember that each alpha I here is non-negative. So basically when this constraint, the constraint number I, is satisfied, here we have a negative term that appears. Since we will be interested maybe in minimizing this quantity, you can already start seeing that those parts of the objective basically are trying to go with the idea that each W here satisfies the constraint. So let's just, for instance, assume for a second that each alpha, there's an alpha I here, which is infinite, for instance. If this alpha I is infinite, then if this is positive, then it will bring down the objective very low, so that will be fine. If on the other hand, so no, let's not say infinite, let's say very, very large. If this alpha I here is very, very large, let's say it's like 10 million, you will see that there is a very high price if this is negative, right? Because I will be basically saying, okay, the objective will be 10 million times something which is negative, minus, so that becomes positive. So there's no way, basically, that this particular constraint here will be violated. Okay? If alpha I, on the other hand, is very low, or alpha I equals to 0, then this constraint doesn't weight upon the objective. Okay? So here I'm really trying to give you an intuitive perspective on duality theory. Each alpha I, each dual coefficient is like a price that you have to pay for violating the constraint. Okay? And again, the Lagrangian here is can be seen as a way to summarize your whole optimization problem. Here you had an optimization problem which was really split between objective and constraints. So objective is the function that you want to minimize, and each constraint is really something that you want to see observed for each x. You really want W transpose xi plus b times yi minus 1 is non-negative. Now if you take a more flexible perspective on your problem, instead of demanding that you minimize the objective with all the constraints are satisfied, you're going to say, okay, I'm going to mix both the objective and the constraints, and I'm going to weight each constraint violation by a constant alpha I, and I have a new problem defined by W and B and those alpha I's. Okay? So each alpha I is now a variable of a problem, but this problem here now takes both the objective and the constraints together. Okay? So once we have defined such a Lagrangian function, what we consider is a Lagrange dual function. So for a second, we're going to forget about W and B, and we're going to focus exclusively on alpha. And the Lagrange dual function is a function which is defined as following. It's for any vector of price is alpha, what is the lowest I can get in terms of W and B? Okay? So given that I have priced each constraint violation at some price alpha I, what happens to this problem here now of minimizing W and B? So if you look at this and this, you can notice that we're minimizing with respect to W and B in each case, right? Here we're minimizing with respect to W and B with some constraints, and here we're minimizing with respect to W and B. But the biggest difference is that there is no constraints here. This is an unconstrained problem. This is just, if you look at this big problem here, what can you see? Well, it's just an order 2 polynomial, right? It's just a quadratic polynomial. This is sum of Wi square, and this is just a big linear term in W and B. Actually, you could write it as W transpose sum of alpha I, yi, xi, plus a term in B, etc., and then a constant. So you have a quadratic term in W, a linear term in W and B, and a constant. So how can we minimize this? Well, this is easy. It's just a quadratic function. You just say that the derivative is 0. You set the derivative to 0. And if you just derivate this equation here with respect to W, well, you will see this term appearing here. This is a linear term. And if you derivate this, well, you just have W. So basically you have W minus this plus some constant. If you derivate with respect to W, you just have this is equal to 0. Just have this is equal to 0. And if you derivate with respect to B, you will have that this is equal to 0. Okay? So what is the value of this Lagrange dual function? Well, the Lagrange dual function is the infimum of W and B. We can actually compute this infimum. At the infimum with respect to W and B of this function, W is equal to sum of alpha I, yi, xi. And you have that because of the first order condition with respect to B, 0 is equal to sum of alpha I, yi. And so if you just use these two equations here and you substitute them here, you will get the minimum of this term. So you get the Lagrange dual function. So let me just go back to what we did. We had a problem which is composed of an objective and constraints. I put the objective and the constraints together by computing the Lagrangian. To compute the Lagrangian, I need to input a cost for each constraint violation, and that's called the Lagrange multiplier alpha. And now I'm going to do kind of the opposite. I'm going to see the problem as a function of alpha, and I'm going to minimize now only with respect to W and B this term here, which is now similar to this. If you look at this and this are similar, except that now this was a constraint problem and this is an unconstrained problem. And it's not just an unconstrained problem, it's just a quadratic function. So it's a trivial thing to minimize. We just derivate with respect to W and B. We set this to 0 and we have this. So this problem now, finding the optimal, maximizing G of alpha, is now called the dual problem with respect to this problem, which is called the primal problem. Okay? So there is a lot of theory in optimization about the relationship between primal problems and their dual. And what happens is that in some cases, solving one is equivalent to solving the other. And even in some cases, and in this case, solving the dual problem, you can recover the optimal solution for the primal problem. So here this applies. So I don't really have the time to go into those details, but what I can tell you is the following. When, in our case, in the support vector machine case, something called strong duality holds. The primal and the dual problem have the same optimum, and we also have something called the Karush-Kuhn-Tucker conditions, which tell us that at the optimum, when I maximize G of alpha, then necessarily, for each alpha I times the constraint is going to be equal to 0. Meaning, if this product is 0, either of the terms is 0. Meaning either alpha I is equal to 0 or this term here is equal to 0. So let me just show you the dual problem, because I didn't write it in the previous slide, but I should write it. If you just take this expression here, and you just substitute to W. So this is we call this G of alpha equals the minimum of this with respect to W and B. So alpha is here and it's here. We just got that necessarily at the optimum, W is equal to sum of alpha I, yi, xi. And then we also have that sum of alpha I, yi is equal to 0. So let's just fit this into this term. Then we have the G of alpha here is going to be equal to, I'm going to write the sum, this norm here is going to be W transpose W, okay? So the norm of W is equal to W transpose W, and that's just sum of I, J of alpha I, alpha J, yi, yj, xi transpose xj, okay? So I'm going to have this big term here, alpha I, alpha j, yi, yj, xi transpose xj, okay? Minus a term which will be basically what was it? So here I will have sum of alpha I, yi, sum of alpha I, yi, I'm going to write I, E here, yi, so it's xj, yj, yj transpose xi plus b minus 1 So basically what I have here is, okay, is this term. But then here what happens is that I have, so let me just see again. Again, ij, alpha I, yi, alpha j, yj. Okay, I haven't done this in a while, so that's why it's okay. It's xj transpose xi, okay, plus, okay, I have it. So it's plus sum of I yi times b plus, so that's probably a minus plus sum of alpha I, okay? This is the sum of alpha I here. So I have, to recapitulate, I have 1/2 times this quadratic term minus this quadratic term minus sum of alpha I yi b plus sum of alpha I. Okay, so this term here, so this term here and this term here are the same. Okay, so except that here it's 1/2 minus 1. So it's going to be minus 1/2. I'm not sure you can see. Well, basically it's going to be minus 1/2 times this term. This term here is sum of alpha I yi b. It's 0 because sum of alpha I yi is equal to 0. And then we only have the sum of alpha I here that remains. Okay? So by substituting these two relationships here, in this we get the minimum, and it's just a little bit of algebra. What we end up having is this function g of alpha. Okay? Now the dual problem is to maximize this function of g of alpha under the constraint that the alphas are non-negative. Okay? And we also have to satisfy the constraint that sum of alpha I yi is equal to 0, because this was given to us by the fact that the dual function here is minimized when sum of alpha I yi is equal to 0. So we need this to define the dual function here. So maximizing this problem here is called solving the dual problem of the support vector machine. Okay? So if you look at this, what is the main difference between this and this? Well, here you have as many constraints as you have data points. So if you have 100,000 points, we have 100,000 constraints. Here we have just first, this is alpha non-negative. This is a box constraint on alpha. And then we have just, this is basically a hyperplane constraint. It's just that sum of alpha I yi equals 0. It basically means that alpha transpose y, the vector of labels, is equal to 0. So it's just, if you want, what would basically it just means that we want the alphas to be in the positive orthant, and then we want them to be orthogonal to a given vector. And the vector is just simply alpha transpose y. We want this to be equal to 0. So in higher dimensions, of course, this is not such this is just from d dimensions we go to d minus 1 possible variables. Okay. So from as many constraints as we had points, now we only have 2 constraints basically. Okay. And the other big difference is is the following. If you remember, in this case, we were looking for a vector W. And W was in which dimension? W is the vector of RD, right? Our points are in D dimensions, so we're looking for a hyperplane. So we're looking for a direction which has the same dimensionality as our points. Here, the big difference by using duality is that we end up solving a problem which has n variables. So we have as many variables as we have training points. So in some cases, we have traded a simpler problem structure here, very simple constraints, for a very large number of variables. So both are quadratic problems. You can see again that this is a quadratic problem with a quadratic constraint and a quadratic objective and a linear set of linear constraints. And this is also a quadratic problem with linear constraints. So on the one hand, we have very simple linear constraints, and on the other hand, we have far larger number of variables usually, because the number of points is usually larger than the dimension. Okay? So which one is better? It's an open topic. It's an open. People think that it's better to optimize directly the SVM in the primal. Other people think it's better to optimize it in dual. But as you will see, it's not just a question of optimization. It also opens the door towards another interpretation of the SVM, which I will give later. And that's the relationship with kernel methods. So again, this is a quadratic program in Rn with box constraints. So again, alpha star can be computed using optimization software, built-in MATLAB or R or Python functions. So the motivation of this is that sometimes for a primal problem, the dual is easier to compute. And so this is a typical example. Then the other thing that is interesting is that the support vector, this dual problem will give us another interpretation. So you might ask, okay, I maximize this program. I get the dual function. Okay? I get the dual function, I maximize it, I get an alpha star, which is optimal. This doesn't give me W yet, right? Well, yes, actually, because if you remember, with alpha star, we can actually recover the original hyperplane. Remember that W is equal to sum of yi alpha I xi. So if I give you the alpha star, you just put a star here, you just give me the optimal dual solution, and this will help me rebuild the optimal W. Okay? B is also given by the solution of alpha star. It's slightly more complicated it's to recover the constant, but it's very easy as well. So what you get in the end is that the SVM that we were looking for, this W and B, is basically this term, sum of I equals 1 to n of yi alpha I xi, x plus b star. So I'm sorry, I should put maybe a star here to indicate that this is the optimum, the optimal alpha. Okay? So by solving the dual problem, we can solve the primal problem. Okay? Again, I will recapitulate once more. We have a primal problem which is split between objective and constraints. We form the Lagrangian which puts everyone together by giving a price to each constraint. We call the Lagrange dual function the problem of minimizing with respect to the initial variables, this pooled, if you want, objective. This is much easier to optimize because there is no constraint here. And then once you have recovered the actual function form, sometimes you can optimize this explicitly, sometimes you cannot. But here we can, because this is just a quadratic function. Then we get the explicit form from g of alpha, and then maximizing g of alpha is equivalent, in this case, to minimizing the primal. And once we have the solutions for alpha star, we can recover the solutions for the primal problem, for W and B. So this is just the way most SVM solvers run. So So if you run libsvm, you will have a problem. libsvm, I don't know if you've heard about libsvm or other SVM solvers. What they try to do is solve this problem. There are specific solvers, algorithms, designed to solve this very quickly. So there is another thing which is, I think, important, is I told you that when you maximize the objective of the dual function, the Lagrange dual function, something known as KKT conditions or Karun-Kushtucker conditions holds. And what do those conditions tell us on the optimum? They tell us that when you maximize this, then at the optimum, necessarily, we have this. Okay? Either this product is 0, which means that either this or this is 0. So what does it mean? Let's think about what does this mean in terms of our original data. If this is equal to 0, what does it mean? Well, it means that the point xi is on the tube. Okay? It means exactly that yi w transpose xi plus b equals 1. And if you remember, basically those equals 1, w transpose x plus b times yi equals 1 means exactly that it's either here or here. So for those points such that this applies, well, usually alpha I is going to be, can be non-zero. It can be strictly positive. On the other hand, if alpha I equals 0, then usually this will not be 0. Okay? So what can you see visually? Well, it's that the hyperplane here that we get is formed by combining all our data points from I equals 1 to n by multiplying each xi by yi alpha I, and you sum them up. And what we have through Karush-Kushtucker conditions is that actually, if yi w transpose x plus b times, yi times w transpose x plus b minus 1 is strictly positive, that is, if the point is outside of the tube, then the contribution to w is 0. Their contribution to w is 0. Okay? Okay, let me just again. If this is not 0, meaning if the point is outside of the tube, not on the line but outside, then necessarily alpha I is equal to 0. If on the other hand the point here is on the tube, then alpha I will be usually strictly positive. I'm saying usually because it's not always the case, but at least those points for which alpha are strictly positive necessarily are on the tube. And all the other points here do not appear when you try to compute w. Okay? So w, the normal vector of this hyperplane, is just a linear combination of this point, and this point. Okay? So why is that important somehow in terms of practical performance? Well, it makes a lot of difference because basically the SVM will not change, the solution to your SVM will not change if you move points which are outside of the tube here. The only thing that really matters to compute the SVM are those points here which are close to the hyperplane. So during the optimization phase, if you want, the SVM will detect those points which are borderline, which are support vectors, and will only use them to form the hyperplane separation here. Okay? This is completely different from, for instance, logistic regression. If you remember logistic regression, each point counts. When you compute the hyperplane of logistic regression, if I change this point here, the hyperplane will change. If I compute linear discriminant analysis, remember LDA, LDA worked by taking a Gaussian, estimating a Gaussian for the white points, estimating a Gaussian for the black points, and then using a linear separation surface, which was basically trying to see which of the two Gaussians had the highest probability of generating a new point. But in that case, if I change this point here, of course, my Gaussian here, estimation for the Gaussian and the mean in particular will change, and so the whole hyperplane will change. In the SVM case, well, you can see that only those points which are close here to the separation area are taken into account. Okay, so that's why people think of the SVM as a kind of robust linear classifier. And indeed, there's a lot of study that has been carried out to show that SVMs can be interpreted as some kind of robust linear classifier with some noise assumptions on the points here, which are corrupted by some kind of Gaussian noise. But it's interesting to see that this is both a feature of the classifier and also a consequence of the optimization problem that we have considered. So remember, I think you probably remember this, so we'll go fast. There is another interpretation of the SVM in geometric terms, which is quite nice. Imagine that we have blue points and red points, which are sets which are linearly separable, meaning that their convex hull do not intersect. This is the definition of linear separability for sets of points. Well, the SVM will just simply compute the two closest points from each set and then take the bisection that passes through those closest points. And the support vectors are basically the extreme points of the facets of those convex hulls. So again, what you can see in this geometric interpretation, which holds, is that if you move points here in this area, you're not going to change the fact that those 2 points are the ones which are the closest to each other. So again, there's going to be some robustness, or basically the SVM is ignoring the area here which is far from the hyperplane. So that's another, maybe a last interpretation for the SVM is that the SVM only focuses on those points which are difficult to classify to form a separation hyperplane. It doesn't really care about those points here which are just too easy, too obvious. It will just focus on that area. So let's now assume that the points, the red points and the blue points are not linearly separable. And actually this is the most common case. It's very rare that a classification problem is linearly separable. If it's the case, maybe the problem is too easy, or maybe there's some overfitting happening somewhere. So imagine now that there's one red point which happens to be on this side and a blue point which happens to be on this side. So of course there's a mistake that you will make by using any hyperplane here. Any hyperplane will incur a loss. So can we try to find an analogy for this maximum margin in the case where the hyperplanes are not, those sets are not linearly separable? Well, the very simple generalization which applies for this case is that we are going to look for a hyperplane which has maximal margin, and when we make mistakes with that hyperplane, we are going to consider how much you are violating the constraint that each red point should be on one side of the tube and each blue point should be on one side of the tube. Okay? So those violations are just simply those lengths here. And so what we're going to say is that we are going to introduce some variables to our program. Since there is no hyperplane that can perfectly split the data, let's on the one hand take into account the margin, and on the other hand take into account the errors made by this hyperplane. And then we're going to minimize these two. Sorry, we're going to minimize a trade-off between the two. So, and what is a trade-off? Well, it's this trade-off is controlled by this coefficient C. So it's easy to see that if you have a hyperplane and you allow yourself to grow the margin as much as possible, you will start making a lot of mistakes. So in that case, by putting both side by side a term which depends on the margin and a term which depends on the errors, you hope to strike a good balance between both. And that's the idea of the so-called soft margin SVM. C is going to control, basically, is going to control this balance. So for instance, if you have a C coefficient which will be very, very large, then the only thing that you will want to look for is a hyperplane which makes as little mistakes as possible. If on the other hand you put a C vector here which is small, then you will disregard a lot of the mistakes and you will just look for hyperplane with a high margin. So let's formalize a bit better this idea of violating the constraints of the separability constraints. Imagine that you have a point here which is x and we have a label y. We're going to call this quantity here, the margin of x and y, the product of the label times w transpose x plus b. So if you remember from the previous slides, ideally we want y times w transpose x plus b to be very large. Okay? Points such that, I'm going back a bit up to here actually, points such that y times w transpose x plus b is very large are points which are either here and white or points which are either here and black. Okay? So for any point, ideally we would like this margin here to be large. And we call this a margin because it's also a margin of basically error somehow. If the margin is very large, then we are pretty confident that the prediction is good, is correct, and the hyperplane works well. So here is one interesting quantification of the error in terms of the margin. We're going to say that the error made by okay, I'm going to write it margin. I'm going to say that as long as a point is on the right side of the tube, that is w transpose x plus b is bigger than 1, then the error is going to be 0. Okay? So I'm not going to really differentiate between the fact that a point is here or very close to the margin here. For me, it's going to be good enough if the blue point is here. As long as it's on the good side, it's fine. So I'm making no error. And then I'm going to penalize linearly when I'm on the bad side of the tube. So this is just 1 minus the margin on the wrong side. Okay? So what does this situation mean here? Well, basically, if a point is in this situation, it means that it's exactly this kind of point here. This point is not only on the wrong side of the tube, but it's also it's even further on the other side of the tube for the blue side. So red points here approaching the tube here are error 0. As soon as they enter the tube, they start increasing their error, and their error now grows linearly with the distance to here. Okay? So this is really, this red length here is exactly the margin for both, it's the error for both, for the red point and the blue point here. So the SVM with the soft margin, so-called the soft margin now, is the following. It's to solve the minimum of W and B of W squared, so the inverse of the margin here, plus C times this quantity here. So this quantity here is known as the hinge loss, basically. The hinge loss between U and Y, this is the hinge loss. And this plays a very important role in the support vector machine with a soft margin. And what you can see here now is that we went from a situation where we needed that W be such that Yi W transpose Xi plus B minus 1 is non-negative. So this was possible when the points were linearly separable. It was possible to find a hyperplane such that it satisfied all of this. And now we've done a bit the same idea as with duality. We are now taking those constraints, taking a soft version of those constraints. And the soft version is just simply to say, okay, as long as this is not too small or below 1, it's going to be, as long as this is going to be bigger than 1, it's going to be 0. But then as this is going to go below 1, this is going to be want this to be bigger than 1. So if this becomes smaller than 1, or even if this becomes negative, then this will become very positive. And so this will definitely incur a price in terms of our classifier W. Okay? So this problem now here is called the soft margin SVM program. As you can see here, this is nonlinear, right? Although this is a program with no constraints, there is a nonlinear objective here. So usually this is quite difficult to solve. So a simple way of reformulating this as a linear program, QP with linear, quadratic objective with linear constraints, where we just rewrite this as this, it's called a slack variable formulation. We basically introduce a slack variable Xi, and we say that this constraint here, the fact that we're using the max of these two, is translated into this constraint. So although for a second we thought that we had a problem that didn't have any constraints, the problem is that it had a nonlinearity here, which made it very difficult to solve. So what we consider again is a problem with quadratic objective and linear objective here in Xi's, and linear constraints in W and Xi's. So I'm not going to go through the derivation of the dual again, but it's very similar to the previous case. So you can again consider a dual multiplier, a Lagrange multiplier for each of those constraints and put them here, and then find the minimum W and B, and then find again a similar condition of W. But in the end, what you will get, there's a slight difference between this dual and the new dual, the previous dual, is that there's a constraint which appears on alpha I, which is that alpha I is smaller than C. Okay? So it's the same form from G alpha, except that now we need as a constraint not only that alpha i's are non-negative, but also that alpha i's are smaller than C. So I'm not going to get into the details, but what we have now is the following. So imagine that we have points black and white here which are scattered. Black and whites are not linearly separable. There is some black here on the side of the whites, and there's a white here which is on the side of the blacks. Basically, the SVM, when you run it with exactly this formulation, so if you run the dual problem with this formulation here, you will end up with 3 cases for alpha I. There will be 3 possible cases. Either alpha I is equal to 0, and in that case, the margin is strictly positive. That is, those guys here are the right side of the tube. Either, so it's not only positive, it's bigger than 1. either alpha I is between 0 and C, and then in that case we have points which lie on the tube, like this. Or the last possible case is alpha I is equal to C. Remember that alpha I cannot be bigger than C, but if it's exactly equal to C, then basically we have all the errors made by the hyperplane. Okay? So in the linearly separable case, there's two cases, 0 or positive. With a soft margin formulation, there's three possible cases, 0, between 0 and C, and C. So what you can see is that the C coefficient here plays a very important role. Basically, C controls how much influence the errors can have on the surface W. If C here is very close to 0, then even the mistakes will not play a very important role. If C goes to infinity, and that's the point of if you let C go to infinity, then basically you don't care anymore about W. The only thing you care is about making as few mistakes as possible, and then you will find a hyperplane that tries to separate by making the fewest mistakes as possible. So here's an really important observation. Why don't we let C go into infinity? I just said that if you let C go to infinity, then you will have a hyperplane which makes very few mistakes. If C goes to 0, on the other hand, you will make mistakes, but you will have a norm from W here, which will be quite small. Well, the idea behind the fact that C should not be too large is overfitting. If you let C go to infinity, then we are overfitting. The only thing that we care about is making as few mistakes as possible. If C, on the other hand, is not too large, then we will try to find a function, a vector W, which has a small norm, basically, and for which W transpose X doesn't move too quickly, if you want. So this is the crucial part in the SVM, and this is the crucial coefficient or parameter for SVMs, which you should never overlook, which is the regularization coefficient. Again, if C goes to infinity, you will make very few errors on your data sample, but maybe you're overfitting. So in terms of geometric interpretation, the previous one still holds a bit. It holds a bit because I think there are some cases where it doesn't really work, but in simple cases it works. So let me just go through this. You remember this drawing, that when you have two linearly separable sets, you can find the SVM hyperplane by taking the smallest distance between 2 points in those convex halls. What is the problem if you have points for which the convex halls intersect? That is, points which are not linearly separable. Then we are in this kind of situation here. In that case, we cannot use the same idea of finding the 2 points which are the closest, because if the two sets intersect, basically there's one point which belongs to both, and the distance is 0. So what we do instead is that we consider the following. We consider reduced convex halls. So a reduced convex hall, so you all know the definition of a convex hall of points. If I have x1, xn, and I call this, what did I call it? Okay, I call it A. Then the convex hull of A is just the set of points, sum of lambda I, xi, I equals 1 to n, such that sum of lambda I is equal to 1, and all the lambda i's are non-negative. Okay? So those are all the possible convex combinations of those points. When you consider something called a reduced convex hull, basically you're going to, I'm sorry, there's a mistake here. Lambda I is non-negative, it's bigger than 0. So if I call this the reduced convex hull with respect to C of A, if the sum of lambda I xi, sum of lambda I is equal to 1, but now I want lambda I non-negative, but smaller than C. So it's the same set of convex combinations, except now I'm putting an upper bound on each coefficient lambda I. So lambda I in the first convex hull here can be equal to 1, meaning, for instance, if I set lambda n equals 1 and all the others equal to 0, then I will recover xn. But now I cannot do this in the reduced convex hull. Why? Because I cannot put a weight of 1 on this point and 0 everywhere else. I can only put up to C. So let's suppose that C is equal to 1/2. In that case, the reduced convex hulls of A and B are outlined here in those small sets here. So what you can see is that if you take a C which is small enough, at some point the reduced convex hulls will not intersect anymore. Okay? So the idea of the soft SVM with a C coefficient, so this is assuming that C is small enough, is that once those two sets do not intersect anymore, you can apply the regular SVM on those two convex hulls and find the two closest points and then find the linear hyperplane. So this is a nice result which helps also visualize the idea of the SVM with soft margin. So let me just follow now with an introduction to kernel methods, which will be brief. So kernel functions. So the word kernel itself is used in a lot of contexts in mathematics. So sometimes people use the word kernel to call the rank space of an operator, kernel as a kernel of integral operators. There's many interpretations. So don't worry if this one is not the one that you knew before. There's even the Linux kernel in computer science, etc. So it's a word that's used a lot. So in this case, it has a specific meaning in machine learning. It basically means the kernel given two points x and x prime in some set. A kernel x of x prime is the dot product of x and x prime when they have been mapped to another space. So so for instance, imagine that I have two strings. Imagine that I map each string to a very long vector, and then I take the dot product of those two vectors. I get a number, and that's going to be a kernel between those two strings. So it seems very simple, but this is a very powerful tool. It basically says that even if X is not a dot product space, even if it's not in Rn, as long as you can find a mapping from X to a feature space, to some Hilbert space, some dot product space, then you can define a function of x and x prime which is just this dot product. So let's take a very simple example. Imagine that this mapping phi of x, imagine that x is a vector, x1, x2. Imagine that this mapping phi of x here is just another vector where I take the squares of each coefficient here. Then the kernel that I would be defining between two vectors is just simply the dot product between those two representations, and that's just simply the dot product of the squares plus the squares. So this is a very trivial and not so interesting example, but I just want to illustrate it so that you see that first we have a point, we map it onto a vector, and then we take the dot product of those two vectors. So here's a very important observation. Yeah, I should have reminded it. Remember this. This is really the only thing that I want you to look at. You remember that the dual problem of the SVM is basically equivalent to maximizing this function here. Okay? So if we look more carefully into this function, what does it depend on? It depends on yi. So each yi and yj is a binary, is a bit. It's a minus, sorry, not a bit. It's a -1 or a 1. And then we have the dot product of xi with xj. Okay? And then once you have defined this, once you have your alpha, you remember that basically your function is just W transpose X, which is basically sum of yi alpha I xi transpose X. Okay? So at both stages of the SVM, in the training phase and in the test phase, the only thing that matters is the dot product of xi with a new point or and, sorry, the dot product of each of your points in the training set with another point, xi transpose xj. Okay? So the only thing that matters is the xi transpose xj ij moving in your training set. This is when you train to get alpha. And then once you have alpha, the function for a new point, x new, is just sum of alpha I yi xi transpose x new plus b. Okay? So this appears in the dual. This here appears in the prediction. So the question is, do I need to know exactly what the xi's look like? Will the SVM consider at any time exactly what the xi's are? It doesn't need to know what the xi's are. The only thing that it needs to know is the value of xi transpose xj and the values of xi transpose x new. So the only thing that matters for the SVM is the dot product of one instance with respect to another instance. Okay? So here is the idea of the so-called kernel trick. If the algorithm only has access to the data in terms of what is the dot product of xi to xj and what is the dot product of xi to a new point, then we can choose any dot product of our liking if you want. And that's the idea behind kernel methods, at least applied here in the support vector machine context. The idea will just simply be, okay, let's just substitute to those xi transpose xj's any dot product between xi and xj, any kernel function of xi and xj. Here I told you that a kernel is basically some dot product. It's not the regular dot product that you know. It's just some dot product between x and x prime in some representation. If I can compute this function, then I can just sneak and put this k of xi and j in my solver, and then at test time, instead of considering xi transpose x new, I would just put the kernel between xi and x. Why is that interesting? Well, it's interesting because if you look at the way I have solved this, not only can I substitute the regular dot product by this new dot product here, but also, in all cases, I never need to have an explicit access to the feature representation of x. The only thing that I really care about is the dot product between phi of x and phi of x prime. So imagine a situation where I design a phi which is a very, very long infinite dimensional vector. So for each, imagine for instance that my x is a, let's say, is a 3D molecule. Imagine that I design a feature vector of infinite dimension, a very, very long feature vector. Of course, I cannot give you the phi of x, this phi of x, because it wouldn't hold in your memory. But now suppose that I have an algorithm which allows me to make this infinite sum when I take the dot product of two infinite vectors. That happens, right? We know, we have in many cases, we know how to compute infinite sums. We have a lot of tricks. For instance, we know that exponential of x is just the sum of xk to k factorial, k equals 0 to infinity, right? We know that. We know how to compute this without having to actually go through the whole sum. So it's the same thing. Imagine that I can find a function here which is equal to the dot product of two very long feature vectors, infinite. I'm writing vectors here, but it's not even a vector. It's just an infinite length descriptor of my data. But imagine that I don't want to give you, or I cannot actually, because it will be too memory consuming. I cannot send you an infinite vector. The only thing that really matters is not exactly this and this. The only thing that matters is the dot product of those two. And that's a function that my kernel can compute. Then in that case, I can formulate the whole problem of learning with kernel functions without having access to the feature vector itself. So I could design very weird, very long feature vectors. As long as I can take their dot products, it's fine. It's enough. So in that context, you can see that the SVM optimization for alpha works implicitly in the feature space. By implicit, I'm saying that it's somehow computing alphas which will work in those spaces of phi's, but without never actually having to compute the phi. And if you look at the optimization that I get here, I get an optimal optimization which only depends on the so-called kernel gram matrix. Here I didn't write. Basically, I told you that in the training phase, the only thing that matters is this, is the xi's, xj's. So this is called the gram matrix. So this is a symmetric matrix. And then you see that here I have a problem which only depends on this gram matrix. So this is Schur's or Adamar's product. It's just the element-wise product of two matrices. And so my dual becomes this problem here. And so if you look again at the dual, it only depends on two things. The product, sorry, the matrix of dot products and the labels wise. And then once I have found the alpha star, I can compute the solution, and the solution will be sum of alpha I, yi, sorry I forgot the yi here, k of xi times the new point that you see. So maybe I can, so I have it here, okay. Let me just first show you briefly why this can be interesting to use nonlinear, to do nonlinear classification. Suppose, so here in this case I will give you explicitly the feature vector, but I will never use it. But I will just give it to you explicitly so that you can see. Suppose I have points x1 and x2, okay, in the plane. And suppose that my feature map, phi of x, goes to R3, okay? And this feature map is a bit tricky. It's x1 square, square root of 2 of x1, x2, and x2 square. Okay? So if I now have 2 points, x and x prime, I will compute the feature map for each of those 2 points, and I will take the dot product. So it's going to be x1 square, x1 prime square, plus this times square root of 2x1 prime, x2 prime. So that will give me this plus this. But actually, if you just compute this, it's very easy to see that this quantity here is just simply the dot product of x and x prime to the square. So actually, this was just for cosmetic purposes. If I just define from the start my kernel function to be square dot product, I get a positive definite kernel which works. And now, suppose, so this is a very canonical example, so you will see it almost everywhere in all the SVM lectures that you will find on the web, but it's interesting. Suppose that my problem, my classification problem is the following. I have white dots outside a circle and black dots inside a circle. So the separation surface is obviously this circle, right? But this is not a hyperplane. So there's no way you can find this directly using the SVM or LDA, etc. But if you use a kernel, instead of using the standard dot product, you use the square of the dot product here, then you will see that there's a way of finding this hyperplane. So again, so here are so this is not done by me, this is what that's downloaded from the web. So the colors are not very clear, but here you should imagine that this is blue and this is red. Here it's not linearly separable. What you do is that you lift your observations from R2 to R3 using this feature map. And then what you can see is that it's easy to have a hyperplane splitting the reds and the blues here in that setting when you have lifted to higher dimensional feature space. So this is a hyperplane R3, but actually when you lift it back, you bring it back to R2, what you get is a circle. So by just simply doing this lifting, you can get a nonlinear separation surface. Okay? But the trick is not so much, in this case, the trick is not so much lifting to 3 dimensions, because this is quite classic in the regression setting. The real trick here is to substitute to the regular dot product the squared here of the dot product. So this is called the polynomial kernel. So the idea, if you want, so I think you're probably familiar with the Trojan horses. So the idea is that if you look at all of this SVM theory, the dual and everything, was just designed as a hyperplane, linear hyperplanes, right? And here we had xi transpose xj. But if we just switch that xi transpose xj and the xi transpose x to a kernel, we can use exactly the same tools, the linear hyperplane separation tools, except that we're doing them in a far higher dimension feature space, but in terms of computations, it's exactly the same. So it's somehow a way of sneaking nonlinear tools in a linear machinery. So time has come, so I will just close to say that why is that useful? Well, it's more useful than just to bring points in 2 dimensions into 3 dimensions and having hyperplanes splitting them, in that case with a circle. There's more applications than that. And it's especially interesting to do that when there is no natural dot product between your objects. So in most of these lectures, our base objects were vectors. We were always assuming that our observations were vectors. But in most cases, in practice, in many cases in practice, you will not have vectors. You will have raw data which will have a structure. So you will have strings, you will have graphs, you will have text, you will have whatever time series of text, time series of graphs, etc. And there's no easy feature representation or vector representation for those objects. In that case, you can use kernel methods. And what does using kernel methods imply there? Basically means that you have to provide a positive definite kernel, a kernel function for objects such as strings, text, etc. So there's been a lot of research to do explicitly that, propose kernel functions for graphs, kernel functions for strings, etc., etc. So I don't have really the time to expand on this, but basically what is important when you define a kernel function is that the kernel function needs to be symmetric, and it has to be a positive semi-definite kernel, meaning that whatever set of points you take for whatever size n, this matrix here always needs to be symmetric positive definite. Okay? So, and I will close on this. So the fact that it's symmetric is important. You can see that it's important that if the dot product, the original product dot product is symmetric, we want the kernel functions to be symmetric also. This kind of makes sense. Why do we need this? Why do we need the positive definiteness? Well, there's many, many reasons why, but there's one that you can easily see here. In the SVM optimization, this is a quadratic function of alpha, okay? And you see that k here appears. What do you know about quadratic functions when you try to minimize them? If the term in x squared is positive, then there is a minimum. If the term in x squared is negative, if you have minus x squared, then there is no minimum. You go to infinity. Okay? Well, in higher dimensions, it's the same idea. We've been discussing this. When a matrix is positive definite, then alpha transpose k alpha is always non-negative. So if k here is positive, so for a second, ignore the labels. This is a Schur product of the Gram matrix with the labels. But just ignore this for a second. If this here is positive definite, then this becomes negative, and then you can maximize. Sorry, my example should have been the other way around. Minus of a function, quadratic function with an x squared term, maximizing a function of parabola, inverted parabola is possible. Maximizing a parabola is not possible. So if this is positive definite, minus this looks like this inverted parabola, and then you can maximize, and then it makes sense. If this is not positive definite, then the result of this might be something like goes to plus infinity. Okay? So to close, a kernel function needs to be such that k is positive definite. So that's the last. So that will be the last slide. So please take your time for the homework. It's going to be online. You will have at least until the end of June to finish it. Do not hesitate to send me questions if you have some, because that homework will be on the slightly more difficult part of the lecture. So thank you very much for those 7 lectures, and see you around. Thank you.